Hello students, I am Dr. Tanmoy Biswas. I welcome you all in my channel Chemistry, the Mystery of Molecules. Today's topic of discussion is silane. Okay, and you can see the structure of silane here. So this can act as reducing agent, and we shall learn about its utilization in organic reaction with mechanism. But before going to details, one MCQ. The question is in front of you, student. I request you please pause the video, try by yourself, and whatever answer you get, please write in the comment box. And don't worry, after some time you'll get the right answer with explanation. Now let's go to the main topic, hydrosilylation. Student, hydrosilylation is actually addition of the silicon hydrogen bond across unsaturated bonds, and in this case both alkene and alkyne can participate and produce alkyl or vinyl silanes. Not only that, aldehyde or ketone can also participate. So, and this is actually called the most important application of platinum in homogeneous catalysis. So this catalyst is first of all platinum based mainly, and second is it's homogeneous. And by the way, I've already discussed about homogeneous and heterogeneous catalysis. Please visit to learn the concept. Now in this case what happens, this addition of silicon hydrogen bond to this carbon-carbon multiple bond, and what it produces, this is the silane, or this regioselectivity I shall discuss after some time. So whenever you counter any question such kind of, please see what reaction is happening and why is happening. Means this hydrogen will be attached to either one of this carbon of this double bond, and these silicon, this R3 part will attach to the other. So this is the very easy hydrosilylation reaction. Now before going to details, I believe you should know what are the sources of all these silicon compounds. Actually the main source is silica or sand. From it elemental silicon is, or this SiH4 is produced. But I have already discussed a dedicated lecture on this topic. Not only that, I have discussed how solar cell gate silicon are produced from this silica. Please visit, it's interesting. So you can see how this reagent are prepared. First, this reaction of methyl chloride with elemental silicon, which produces this trimethyl silyl chloride, TMSCl, silyl enol ether protection or enolate trapping, I have already discussed. Me2SiCl2 or dimethyl dichlorosilane. What is its application? Preparation of silicones, means this polymer. It's very useful. So in this way other silicon based compounds are also produced. They are very useful. Now not only that, silicon tetrachloride, it could be prepared from the reaction of this silicon and chlorine. It will produce this silicon tetrachloride, and if you react this silicon tetrachloride with ethanol, it will produce tetraethoxysilane more specifically, and this tetraethoxysilane could further react with this phenyl magnesium bromide, and in this case stoichiometry obviously important, and this phenyl group will be migrated to one silicon, and this one OET will leave, and ultimately it will produce this PHSiOET. Later on, in presence of 3 equivalent of lithium aluminium hydride, which is actually a source of hydride, means nucleophile, so it will produce this phenyl silane PHSiH3, and ultimately this part. So this is the overall reaction to prepare different type of phenyl, means different type of silane, or more specifically if I say this silicon hydrogen compounds, which we will use after some time. Now so let's come back to the mechanism of this hydrosilylation reaction, of which is named as Chalk-Harrod mechanism. So what happens in this case? First, this silicon hydrogen compound get reacted with this metal, mainly for example make consider platinum, zero oxidation state, and ultimately produce this product, and this is called, student, oxidative addition. Okay, and remember that catalysts which are capable to undergo or capable to bring about this hydrosilylation reaction, they are also capable for hydrogenation reaction of alkene. Similar chemistry, means alkene will bind to this metal center in this way. In the next step, this hydride will be transferred from here to this metal center, and after that there will be a sigma bond formation between metal and alkene. This, and in the last step is this part is actually, student, reductive elimination. So in this way this terminal silicon attached silane could be produced if you use terminal alkene obviously, and another thing, that is the production of this main catalyst, means regeneration of the catalyst, and in this way the catalytic cycle will continue. And in this context, one important information is this addition proceed via anti-Markovnikov pathway, means the silicon get attached to the terminal carbon. By the way, you can remember this phenomena a little easily, that for Markovnikov addition you can say this HI addition. This I is the negative part, so it will attach to this. Now if you take this hydrosilylation, which one is negative? Hydrogen and silicon. So obviously this part is negative because silicon is relatively less electronegative. So similar way you can consider this negative part will attach here. So this way will help you to remember the chemistry easily. Okay, this is the strategy, means the negative part will attach in a similar way. Okay, although in this first case the hydrogen is delta positive. Now let's come to the catalyst for hydrosilylation reaction. So this is actually a typical reaction for hydrosilylation, although in case of platinum catalysis there are some byproduct formation possible, means alkene hydrogenation is the side reaction of this hydrosilylation, means alkane formation, and second is alkene isomerization, third is vinyl silane. Originally there was a goal of addition of this HSI to this carbon-carbon double bond, but in this case you can see addition happened after that hydrogen elimination to produce this alkene derivative. So these are side reaction. Not only that, platinum leaching or platinum nanoparticle formation is also a major issue. But by the way, although this leaching is very less, but remember student, this hydrosilylation is done in industry extensively. So since it is done in very large scale, so small amount of platinum leaching will also end up in a big consequence ultimately. So that's why it is highly important to use proper catalyst such that the leaching is less. So you can see simple this Pierce catalyst here, and in this case this is Kerstedt catalyst, and in this case you can see this platinum is attached to 3 alkene and this platinum is in zero oxidation state. But the better one is this Marcos catalyst, because this platinum is attached to this N-heterocyclic carbene. I shall discuss the importance of this carbene after some time. So there are mainly these 3 catalysts, although there are some other catalysts, like you can see this rhodium catalyst, this Wilkinson catalyst. Not only that, this is ruthenium catalyst, Graf spugenation catalyst. So all this type of catalyst can also participate in this hydrosilylation reaction. They are capable. Now let's come back to the topic, that is Marcos catalyst. Why this is important? Remember student, in heterocyclic carbene they are actually singlet carbene, means this lone pair of electron is in sp2 hybridized orbital, and they also have a vacant p orbital. So they can donate the metal center via this sp2 hybridized orbital, and they can accept excess electron density from the metal center by this vacant p orbital. So because of this donation and acceptance, this carbon platinum bond is multiple bond character and it is relatively stronger. So if this bond is stronger, the probability of leaching is less. So that's the uniqueness of this N heterocyclic carbene ligands, and if you can reduce the platinum leaching, huge amount of money could be saved. Now let's discuss few examples. For example, this is first example using this Marcos catalyst, and this is a simple hydrosilylation of this silicon hydrogen bond across this double bond, and silicon goes to the terminal position. Similar thing you can see in this case also, but the interesting part of the second example is that, see, the epoxide group is intact. Generally we say that epoxides are very strained molecule, 3-member, being highly reactive. It's true, but the reaction condition is mild as well as selective, such that selective hydrosilylation could be achieved. So this is the overall reaction, and you can say similar mechanism just sometime before we have discussed, like this oxidative addition, group transfer, reductive elimination, and ultimately in this way the catalytic cycle goes on. Now let's discuss the alkene hydrosilylation. Student, alkene has 2 pi bonds. So if you do the hydrosilylation, for example this terminal alkene, so what it will produce? Vinyl silane, and in this case 3 types of vinyl silane preparation possible, and if you take the internal alkyne, 4 types. Now let's discuss few real examples. First example is the reduction of alcohol to alkene, and in this case this silicon hydrogen bond is reducing agent. And by the way, the interesting point in this chemistry is that this compound has one silicon hydrogen and chlorine. By the way, remember both silicon hydrogen and silicon chlorine are not that much stable bond, but silicon oxygen bond is very much stable, and that is the driving force. Why? Because this oxygen silicon bond, if you look at it, is actually apparently looks like it's a sigma bond or single bond, fine, but there is some other stabilization. What do I mean? The lone pair of oxygen in the p orbital could form efficient overlap with the energetically accessible vacant d orbital of silicon. So this lone pair of electron could be donated to the silicon side. So although it looks like a single bond, it is actually not a single bond. It has some partial double bond character, means relatively stronger bond. Fine. So if this is a stronger bond, so it will prefer to form, and you can see in this case of silicon there are two silicon oxygen bond, means it's more stable. So that is the driving force for this reaction. Now silicon oxygen, sometime before, like in the talk of this silyl enol ether preparation or enolate trapping, we have learned that oxygen can act as a good nucleophile and it can replace the silicon chlorine by SN2 type reaction, and ultimately this is produced. This is, student, silyl ether you can consider. But these oxygen, this hydrogen can transfer, but this oxygen is not a good leaving group. Okay, so in order to make this a good leaving group, this indium 3 chloride is used, which is Lewis acidic in nature, and it binds to the oxygen. See here, and after this binding, this oxygen becomes a relatively better leaving group. So this hydride is shifted here, it opens, and ultimately it produces this alkene. So, and if you look at the reaction condition, this is DCM or DCE, dichloroethane, 80 degrees centigrade, 30 minutes to 6 hours, that much milder condition. And in this case, the silicon hydrogen bond is actually the reducing agent. Now, a question may come in your mind that how this is hydrolyzed, or I request you please recall the silyl ether hydrolysis by different reagent. I have already discussed this thing in a dedicated lecture about silyl enol ether. If you have any doubt, you may visit, I shall provide the link. Now let's discuss the second example, that is reduction of carbonyl compound to alcohol. And in this case, these are the catalyst. As some time before I told what is the role or uniqueness of this in heterocyclic carbene. So you can see that's why all are almost, except this one, heterocyclic carbene based catalyst. And in this case, this manganese center is actually the catalytic center. By the way, sometime before I have told that platinum is one of the best catalyst for this purpose. So the question that why manganese is used? Actually, student, platinum is not that much widely available, point number one. Second, it is extremely costly. So if this platinum could be replaced by more cheap earth abundant 3D transition metals, then that is best for industry. So that's why this third row transition metal catalysts are utilized. So they are actually reducing agent, and this silicon hydrogen is actually they are actually the catalyst, and this silicon hydrogen is actually the reducing agent, means this hydride will transfer here, and ultimately what it will produce? It will produce a silicon, means I'm not showing other substitutions, so it's silicon ether. This is called silicon ether, and that hydrolysis is done by H+, and ultimately it produces the final, for example, this R1 R2 both alkyl, then you can consider it's a secondary alcohol. So this is actually carbonyl reduction to alcohol. Not only that, the derivative of carbonyl, that is amide reduction to this amine, and by the way, in this case 2 equivalent of silicon needed. Why? Because this carbonyl is replaced by 2 hydrogen, and you can see this, that 2 equivalent of silicon hydrogen needed, or SiH bond needed. And in this case, first this H attacks here, ultimately it opens up, and in this case, students, still iron as catalyst, third row transition metal. So first this silicon ether is produced, but here the interesting point is that this nitrogen attachment, it has lone pair, so it can push and this OSI can leave and ultimately produce this iminium type derivative, and this is also electrophilic like the amide. Okay, so this is electrophilic. So next step, this silicon hydrogen will act as a nucleophile, means attack this center, it will open up, and ultimately this final product will be produced. And see here, what is the final product? This oxygen is attached to 2 silicon. Okay, means in this way the oxygen got stabilization and 2 silicon also got stabilization because of their bonding. Now let's go to the third example, that is imine reduction to amine by sometime before iminium, now it's imine. And in this context, this catalyst is used, BC6F5 thrice. This is, student, actually a very strong Lewis acid of boron, and this use of such kind of concept is called FLP, or frustrated Lewis acid base pair theory. I have already made a dedicated lecture, please visit, because this concept is very new, so I think you should learn. This boron center actually little bulky center, because this pentafluorotriphenyl group there. So this is a bulky center, so only small molecule can approach, but it is very high Lewis acid. Consequently, what happened? First step, these boron reacted with this hydrogen from this SiH bond. Why? Because as I told sometime before, because of the electronegativity difference, these hydrogen is delta negative, means hydride type, and boron is electron deficient. So these hydrogen can donate some electron density to boron center and get activated. So what happens after this? So these hydrogen could be abstracted to this boron side, and ultimately it will produce, this is silicon, this is 2-methyl, and 1 is phenyl, and this is cation, point number 1. So in this way, this boron hydrogen complex, this bond will be produced, and this is, student, actually the nucleophile. And this silicon is in plus, means carrying a plus charge, and there is nitrogen. Remember, oxygen and nitrogen belongs to the same row of element. So bonding between the silicon and nitrogen have similar type of stabilization. So this nitrogen lone pair will coordinate to the silicon center, and after this coordination, see, it is carrying a formal positive charge, means these carbon center became more electrophilic. So what happens? This hydride will attack here. Okay, it's actually hydride because it is delta minus. So it will attack and it will open, and ultimately this imine reduction will happen. And in the next step, this is a hydrolysis to get the final product. Okay, obviously written after purification, and see the yield up to 97%. So that is the uniqueness of this reaction, or silicon, this Si hydrogen as a reducing agent. Not only that, this FLP concept, this boron reagent. Now the last type of example, that is polymerization reaction by hydrosilane. Now sometime before we have learned that silicon hydrogen bond could be added across a carbon-carbon double bond. Now if these two molecules are in the same, means two groups are in the same molecule, obviously don't expect that intermolecular reaction will happen, because intramolecular reaction will end up 4-member ring, that is strain. So what it will result, means, sorry, not 4-member ring, the transition state in 4-member ring, but the product will not be that much stable, because in this way there will be a silicon, this double bond, which is not stable. Okay, silicon carbon double bond, not stable. So it will undergo intermolecular reaction, and ultimately it will produce this polymer, because N is there. This is the silicon based polymers. Sorry. So in the next example, you can see that both alkene and hydrogen, they are in different, so they can combine together. Okay, so you can consider that this is a boy having 2 hands, and this is a girl having 2 hands, and in this way this is another girl having 2 hands, this is another boy having 2 hands. So they are holding their hands by this hydrosilylation reaction. So you can consider this is, so in this way, so they are forming a chain, and in this way this is also a chain type polymer. Okay, so not only that, another type of example is alkene, dialkyne polymerization using this 2 silicon H. So it will react with 2 this alkyne, and ultimately it will end up in the final polymer. Now sometime before we have seen during this reaction, this PMHS was used as a reducing agent, not only in case of this silicon hydrogen bond, because this PMHS, the structure is this one, you can see, and in this context you can see there is a silicon hydrogen bond, and that can act as a reducing agent. Although it's a polymeric material, but it is capable to do that. And actually how this is produced? This is produced by the reaction of this methyl dichlorosilane with water, and ultimately this molecule is produced. Actually, it is used in organic chemistry as mild and stable reducing agent which easily transfer hydride to the metal centers and a number of reducible functional groups. And this is interesting because it is a byproduct of the silicon industry or waste of the silicon industry. So using chemistry, we are utilizing a byproduct into normal reaction. That means that should be appreciated from green chemistry point of view. It will reduce the chemical pollution. So that's why this is interesting. Now in conclusion, what you have learned today, that silicon hydrogen SiH bonds can act as a source of hydride and behave like a reducing agent. You may consider there, I shall explain something later on about this BH, boron hydrogen versus silicon hydrogen. Now hydrosilylation can behave similarly as hydrogenation of alkene, and majority of hydrogenation catalysts are active for this hydrosilylation reaction. Now platinum is the most active catalyst for this commercial hydrosilylation reaction, and these N-heterocyclic carbines can bind with platinum strongly and resulted in relatively more stable catalyst which will eventually reduce the platinum leaching. Finally, the alkyne hydrosilylation reaction also possible for, this hydrosilylation reaction is also possible for alkynes, and in this case the product is vinylsilane. And the last one is silicon hydrogen can reduce not only double carbon-carbon double bond, it can reduce keto, amide, alcohol, etc. functional groups also. Okay, so let's come back to our MCQ. What is the product of this reaction? So you can see this is actually, student, a boronic acid. There is a boron oxygen bond, and in the reagent what is taken, this potassium hydrogen fluoride, means this is, you can consider a source of fluorine. Now if you compare the stability of boron oxygen versus boron fluoride, which is relatively more stable? Obviously boron fluoride, because this fluoride has 3 lone pair of electron, oxygen has 2, and these 2 belongs to the same row elements, so overlapping is good. So in this case what happens, this fluoride acts as a nucleophile and this OH leaves. So ultimately reaction happens, and what it produces? It produces PHBF2. But reaction still does not stop here, because still this boron is a 6 electron species or sextet, and in the reaction medium again fluorine is there. So first it will produce this fluorine tri-substituted with a negative formal negative charge on boron. Now this part we have understood, and in the second phase this excess fluoride is taken because this is a negative charge carrying this fluoride. Now TMS means trimethyl silyl chloride. We know this silicon fluorine bond is exceptionally stable. Same reason. Sometime before I explained for silicon oxygen bond. Similar reason, this is stable. So that's why this extra fluorine is taken, and ultimately it produces this ARBF2. Okay. So in this case the answer is, this is fourth option. So this is the end of the discussion. Thanks for watching. I believe this video may be useful for you. Please write your opinion in the comment box, and if possible please visit my another channel. So stay happy, stay blessed. See you in my next video. Bye bye.